Welcome to Math Surge. Today we are going to talk about the corollary of theorem number 3 or the inverse statement of theorem number 3. Now, if you can remember, while we were doing straight lines and theorem number 3, I told you that the corollary or the inverse statement of theorem number 3 is also true, which means that the corollary of theorem number 3 is also a theorem itself. But we didn't try to prove the corollary of theorem number 3. There was a reason, because we didn't have enough data to prove that theorem. That is why we are studying this corollary of theorem number 3 under triangles. We need some acquired knowledge from triangles to prove this corollary. That's what we are going to do now. So before we study the corollary, let's go back to theorem number 3. Let's see what theorem number 3 says. Now theorem number 3 says, if there are two parallel lines and they are intersected by a transversal line, the resulting internal alternate angles are equal. The resulting corresponding angles are equal, and the sum of internal angles on any given side of the transversal is 180 degrees. That is what theorem number 3 says. So now we are going to look at the corollary of theorem number 3 or the inverse statement of theorem number 3. This is what the corollary of theorem number 3 says. If two lines are intersected by a transversal line and if the resulting internal alternate angles are equal or corresponding angles are equal or the sum of internal angles on any side of the transversal is 180 degrees, then the said two lines are parallel. I repeat, if two lines are intersected by a transversal line and if the resulting internal alternate angles are equal or corresponding angles are equal or the sum of internal angles on any given side of the transversal is 180 degrees, then the said two lines are parallel. That's what the corollary of theorem number 3 says. Now, have you ever wondered why they have used this word connector or? The reason is, you can see that there are three requirements: internal alternate angles being equal, corresponding angles being equal, and the sum of internal angles on any side of the transversal being 180 degrees. What this or says is that if any of these requirements are met, then automatically these two lines are going to be parallel. That is why they have used or in this statement, in this inverse statement of theorem number 3. Okay. Now this is what the theorem says. Let AB and CD be two straight lines in the same plane, and let EF be a transversal which intersects both AB and CD, right? Now let us assume that the magnitude of this is alpha and this is beta and this is gamma and this is theta. Okay, what the theorem says is, what the corollary says is, if alpha is equal to beta, AB is going to be parallel to CD. If gamma is equal to beta, right, because alpha and beta, they are any two corresponding angles. Okay, we have randomly selected these two angles, right, and gamma and beta, right, if gamma is equal to beta, AB is going to be parallel to CD, and if the sum of beta and theta is going to be 180 degrees, then also AB is going to be parallel to CD. Okay, so we are trying to prove this. Now, how can we prove this? Can we get any help from the axiom of parallelism. What does the axiom of parallelism says? Now, axiom of parallelism says if two lines are intersected by a transversal, and if the sum of internal angles on any given side of the transversal is less than 180 degrees, then these two lines are going to meet one another on the same side if extended far enough. Okay, now that's not going to help us, right? That's not going to help us to solve this, to prove this theorem, this corollary. So what can we do? Can we get any help from theorem number 3? No. Theorem number 3 only talks about two parallel lines being intersected by a transversal. So it seems like we need something new. Now we are going to see what that something new is. Okay. I am going to introduce you to a new term called lemma. Now a lemma is, I think they have borrowed this, the mathematicians have borrowed this term from ancient Greek. A lemma is a true statement or a minor theorem which itself does not have a major impact on that particular mathematical field, but it would help mathematicians to prove certain major theorems. That is what a lemma is. So we would like to consider a lemma a minor theorem. Okay, a minor theorem. So we are going to look at lemma number 1, right? What is lemma number 1? Lemma number 1 is the sum of any two angles of a triangle is less than 180 degrees. Okay, the sum of any two angles of a triangle is less than 180 degrees. Intuitively, when you see this statement, you know that it is true. Why? Because we know the sum of all three angles is 180 degrees. Of course, then the sum of any two angles must be less than 180 degrees. But mathematics does not work that way. We need to prove this statement in a kind of a rigorous manner. So now we are going to do that. Okay. Assume that ABC is a triangle. Okay, and we have extended side AB to some external point D. Okay, so let us say that the magnitude of this is alpha, this is beta, this is theta, and this is gamma. Okay, so now we know that gamma is, I'll use this color. We know that gamma is equal to the sum of theta and alpha. Okay, from theorem number 5. Okay, from theorem number 5. As a result of this, we can safely say that alpha is less than gamma, because gamma is the sum of both theta and alpha. Therefore, alpha must be less than gamma. Okay, so we will write it here. Alpha must be less than gamma. Now, we are going to add beta to both sides of this inequality. Alpha plus beta then must be less than gamma plus beta. Alpha plus beta must be less than gamma plus beta. Now we know that gamma plus beta is 180 degrees from theorem number 1. They are adjacent angles. Okay, therefore the sum of alpha plus beta must be less than 180 degrees. Okay, similarly, if we can extend AC to some external point, we'd be able to prove that the sum of theta and alpha is going to be less than 180 degrees. And if we extend CB to some external point, then we'd be able to prove that the sum of theta and beta is also less than 180 degrees. That way we can prove that the sum of any two angles of a triangle is less than 180 degrees. So we have proven that lemma. Now let us see how can we use lemma number 1 to prove the corollary of theorem number 3. Okay, this is how we do it. We will draw two lines AB and CD being intersected by a transversal EF at G and H respectively, such that the sum of BGH and the sum of GHD is 180 degrees. So we have constructed AB and CD being intersected by EF such that the sum of BGH and GHD being 180 degrees. Now mind you, if the sum of, now this is the right hand side of the transversal, if the sum of the internal angles on the right hand of the transversal is equal to 180 degrees, then automatically it makes the sum of internal angles on the left hand side of the transversal also being 180 degrees. Okay, so it doesn't matter if we choose this side or this side. Now this is a fact. Now we will assume, now what are the two possibilities, right? Two possibilities is that AB and CD, these are the two possibilities. Possibility number 1 is AB being parallel to CD. The second possibility is AB not being parallel to CD. These are the only two possibilities. Can you think of any other possibility? If AB and CD are in the same plane, then these are the only two possibilities. Okay, these are the only two possibilities, right? So now we will assume this second assumption is true. Okay, we are going to assume that AB and CD, they are going to meet one another if extended to the right of the transversal far enough. Okay, so our assumption is we are going to assume that AB is not parallel to CD. That is our assumption. So what would result in? This would result in this. Let's say AB and CD, they meet one another at some point I. Okay. Now because of this, you can see that GHI is a triangle. Okay. Therefore GHI is a triangle. Okay, because they meet one another. Now because GHI is a triangle, the sum of, from lemma number 1, the sum of BGH and GHD is going to be less than 180 degrees from lemma number 1. Now is it possible? Is it possible? No, because we have constructed AB and CD in such a manner, the sum of BGH and GHD is going to be 180 degrees. But we assume this, that AB is not being parallel to CD. We arrive at this conclusion, which is not possible because it contradicts this. It contradicts our very construction. This is not possible, right? So the only possibility is AB being parallel to CD, QED. So we have proven that if two lines are intersected by a transversal and if the sum of internal angles on any given side of that transversal is equal to 180 degrees, then these two lines are going to be parallel, right? That's what we have proven here. Now we are going to prove that if the first requirement is fulfilled, AB is going to be parallel to CD. What is the first requirement? If AB and CD are two lines intersected by a transversal, and if the resulting any of the interior alternate angles are equal, then AB is going to be parallel to CD. We are going to prove that. Let us assume that these two internal alternate angles are equal. So this is alpha, this is alpha. If this is alpha, this is 180 degrees minus alpha. This is also 180 degrees minus alpha, right? Now if you add these two, the sum is going to be 180 degrees, because this is 180 degrees minus alpha plus alpha. This is also 180 degrees minus alpha plus alpha. The sum of the internal angles on this side is also going to be 180 degrees. Now we have already proven that if two lines are intersected by a transversal and if the internal angles on any given side of the transversal is 180 degrees, then these two lines are going to be parallel. So if we assume any of the internal alternate angles are equal, automatically the third requirement is fulfilled, right? So AB must be parallel to CD. Similarly, we can prove that if any two corresponding angles are equal, we will select randomly these two angles, okay? This is going to be alpha and this is also alpha. If this is alpha, this is 180 degrees minus alpha, right? So again the sum of these two angles are going to be 180 degrees, which proves the fact that AB is going to be parallel to CD. So that way we can prove the complete statement of the corollary of theorem number 3. Now you may ask, what is the importance of the corollary of theorem number 3? Sometimes you get problems where you are asked to prove any two given lines are parallel. So when solving such problems, the corollary of theorem number 3 is going to be of immense help to you, right? So please remember that. With that, I come to the conclusion of this video. Thank you for watching and please subscribe.